Okay, everyone, good afternoon. Let's start. Just quickly go over what we did last time for chapter for lecture 8. So we did again. It's a kind of construction by using compasses and the ruler. Okay, lunar straight edge. So construct a right triangle ABC such that the altitude to the hypotenuse and the medium to the hypotenuse have given. Okay, we have R and S. We give you two 9 segments R and S, and those R and S will be the altitude and the medium of a right triangle. Okay, to the hypotenuse. So here's what we want here. That's the picture I'm looking for. Where so how can we do this? How we can construct that? Okay, where let's see. The key idea is that where we know how to construct the right triangle, so we can do the small triangle, right? CHO. We can do the small triangle. That's from earlier, right? We have the H air. We know H, we know air. There's no problem. We can construct triangle. And then the next question is that where how do you construct the A and B? Now we use the idea that for any circle, if AB is a diameter, right, then any point C on the circle can form a right triangle ACB, right? So angle C is a right angle. So what can I do here is that I just go from the O here. O is the I choose O as a center, and then CO as the radians, right? And then I can draw a semicircle, right? And then intersect the baseline at the A and B, and then we can get the right triangle, right? We can get that. Okay, next one. So what is this one? This is tricky. I like this question a lot. So you have a square here, and then you have a 9 segment of name 3, right? And that's just like a stick here. The stick is moving, right, inside the square, so that both A and B have to be on the boundary. And then I'm looking for the midpoint P, right? So what's the behavior of the midpoint P, right? Does it make sense? Construct the nucleus of the midpoint P, right? When the AB is moving, right? And then this just use the same idea, right? So if AB is the diameter of a circle, then the ACB is always the right triangle, right? And so the CM, right? CM is just half of the AB. So it turns out that the M, the midpoint, right? The nucleus of the M of the midpoint is just the following, right? It's just a following picture here, right? The green line, right? The green dots, all of them, the green line, right? So at the corners, they are just a part of the circle, right? It's just a quarter of the circle, right? 4 of them, right? So that is this. Why? Just because CM is a fixed number. CM is always half of the AB. Okay, that's very nice. And now here just ask you to construct the square root of integer. Why do we need that? Because that's a preparation when we try to get the regular polygon, right? So how to get the square root of n? N is the integer, right? You can do this. Okay, the next one, and because of that, I can do the average, right? If R and S are given, how could I get the average? There are two types of averages: the mean, the AM, and the GM, right? So arithmetic mean just means R plus S divided by 2. That's an easy one, right? Just put the R and S together and get the midpoint. Now, how do I get the geometric average, right? In other words, I'm looking for the R times S and take the square root. Now, for this one, you can use this idea to do it. So the basic idea is that I want to show the CD square is equal to AD times BD. So you can assume your AD is R and BD is your S. Then the altitude is just a geometric average of R and S, right? So if you know the idea, the rest of them should be okay. And now the main part for last time was to construct a regular polygon, right, of inside. And we tried to work for 5 and 10, and last time we did for 5. So for 5, no, for 10, I mean. For 10, basically, let's see, you have a unit circle, right? The radius is equal to what? How do I find the length of the side for the regular polygon of 10 sides. Now you look at the three square, the small square, right? The angle on the top is 36 degree. Why? Because 360 divided by 10. And so it's an isosceles triangle, and the base angles are 72 degrees and 72 degrees. So the question here is that suppose I give you a triangle of 36 degrees, 72 degrees. The two sides are given by one, and then what's the other one, right? How to get that? And the picture on the right give you the idea. I'm not going to repeat that, but you know this. So it's a similar triangle, and eventually you get the x value is equal to this. So in other words, that's the number I'm looking for, right? If I can construct the square root of 5 minus 1 divided by 2, then I can finish my construction for the regular polygon of 10 sides. Does it make sense? That's the idea. Okay, so how to do that? Well, if you know the computation, the rest of them will be just fine. You just try to figure out how to get the square root of 5, right? How to get the square root of 5. So the square root of 5 is, let's see, is in this way, right? You get a regular, you get a unit circle, right? And then m is the midpoint, so that's 1/2, right? So this part is 1/2 here, and that part comes up with the square root of 5, right? Square root of 5 divided by 2, and then this is what we are looking for, right? So this is what we are looking for. So this is a square root of 5 minus 1 divided by 2. So that's the length for the regular polygon of length 10, of length 10. Okay, any question? Any question? Now today I'm going to first work on the regular polygon of length 5, right? Length 5. So what can we do here? And basically, well, let me first give you the conclusion, and then we are going to show the proof in my next next page. Okay. So the key idea is actually, so this is the length of the this is the length of the is a side length when n equals 10, right? It's a regular polygon of 10 sides. So this is that. But actually, I can also get the side length of regular polygon of 5. It's a regular pentagon. So this is actually the side length. This is actually the side length when n is equal to 5. So that's very nice, right? For this right triangle here, one side give you the side length when when the number side is equal to 10. The other side give you the number length when the number when n is equal to 5. It's a regular polygon, regular pentagon, right? And you may wonder why, and I'm going to prove this. So basically, you can prove this. Okay, so first of all, what is that side? What is that side? Well, for this side here, it's a Pythagoras theorem, right? So it's a square root of, right? It's a square root of the one square and plus the denominator, plus the other side. So it's a 5. Square root of 5 minus 1, and you take a square, right? And it's a little bit tedious, but after we finish that, okay, so let's try to finish that. 1 plus, this is 4 here, right? 5 minus 2 times root 5 and plus 1. So we can get this one here. And the whole thing is 4 here in the denominator. And the numerator is 5 plus 1 is 6, right? But there's another one at the beginning. So it's actually 10 minus 2 root of 5. And then take a square root. So this is the length of this side. Okay. And in my next page, I'm going to prove that this number is actually the side length when we talk about the regular polygon, regular pentagon. Okay, right? So we are going to do that later. Okay. So far, so good. Okay, so now I'm going to switch to lecture 9. Okay, for the lecture 9, uh, try to finish it. Okay, so I want to figure out suppose you have, so the first question for today is that I want to find the length, find the side length the side length of a regular pentagon, right? Pentagon, right? Inside a regular a unit circle, right? I want to find that. Okay, well, how could I do that? Well, I'm going to work on that in terms of the problem we did the last time. So some time ago, actually, we have such a picture here, right? So this is a unit circle. Okay, for this unit circle here, and this is 36 degree, right? So this is 36 degree, and I get another 36 degree. Okay, so that's here. And then this side should be my regular polygon, regular pentagon, right? So it's a AB. So basically, I'm looking for the AB. You see that? So AB is the side length of the regular pentagon. Okay, inside inside the unit circle. All right, and this is a x here. This is right triangle, and assume this is x, and this should be the 1 minus x. And this side is the number we did earlier last time. Square root of 5 minus 1 divided by 2. Does it make sense? So that's the number we did earlier, right? So that's here. Root 5 minus 1 divided by 2, right? Okay, so let's do this. Everyone's okay? So based on this picture, I want to figure out what is AB, because AB is just the length, side length of the regular pentagon. Okay, actually, it's not bad to figure out that. I'm going to get this, so A, B, let's say C here and D here, okay? I'm going to work on the AD square in two different ways. So I'm going to get the AD square in two different ways. Okay, the first way is that I can go from this right triangle, right? From this right triangle, then I can get that it's actually 1 square minus the x squared, right? So this is one side. This is AD square. But for the other one, I can also go to the other right triangle. So let me use the yellow one here. So if I work on here, I can get, let's see, the other one, I can get the square root of 5 minus 1, take a, divide by 2, and this one take a square, and minus 1 minus x squared. Does it make sense? Okay, give everyone a few seconds, right? You have two right triangles, and AD is a common edge in the two right triangles. So you can figure out the AD by using two different ways, right? And so you can simplify that. Okay, so let's do the right-hand side. So this is equal to 4. 5 plus 1, that's 6, minus 2, root of 5. Okay, minus the other side here, it's a 1 square, x squared, and minus the 2x. Okay, right? We can get that. And now, so let's see. I'm trying to simplify that. So that is equal to. Uh, Wait a second. Well, let me just try to simplify that. So it's actually 2 here, 3 minus root 5. I cancel out the 2 from the numerator and the denominator, right? Minus 1 minus x squared plus the 2x. Good. The good news is that x squared cancel with that x squared, right? X squared cancel with that x squared. So I can get the 2x. So what's my 2x here? 2x is actually, right? So 2x is here. 2x is actually, so I'm going to get 3 minus root 5 over 2. We'll actually switch that. Sorry, it should be, let's see, switch this, right? I should move the 1 to the other side. So this 1 should be moved to the other side. So 1 plus 1, right? And then minus 3 minus the root of 5 over 2. So I can get 2 here, right? And 1 plus 1 is 2, and 2 times 2 is 4. 4 minus 1, that's equal, 4 minus 3, that's equal to what? 1 plus root of 5. Okay, so your x value is actually 1 plus root of 5 divided by 4. Okay, that's your x value. And after you get your x value, then you can get the AB. And we are almost done. So what's my AB here? My AB should be 2 times the AD because of symmetry, right? But how could I get the AD? Where AD, I just use the formula, the Pythagoras theorem, right? The first, according to the first triangle, so it's a 1 square minus the x squared, take the square root, right? It's a Pythagoras theorem. So you're going to get 2 times, you don't need that, 2 times the square root of 1 minus 1 plus root of 5 divided by 4, take a square. I know it's tedious, but it's not too bad. Okay, it's not too bad. So we get 2 times. Uh, well, let me just move the 2 inside. So if I move the 2 inside, means it's the 4 here. Can you see that? So it's actually the following. So it's actually the square root of 1 times 4, that's the 4 here, right? And minus the denominator is supposed to be 16, but 16 times 4, don't forget the 4. You have a 2 outside. So I can move the 2 outside, becomes 4 here. So the denominator becomes 4, right? The numerator, what's the 6 here, plus 2 times root of 5. And then if I just work together, this is the denominator 4 here. The numerator, 4 times 4 is 16. 16 minus the 6, that's equal to 10. And plus 2, actually it's minus, right? 10, it's minus 2 root of the 2. And this is actually 1/2. I can move the denominator to outside, so it becomes 1/2. And then square root of the 10 minus 2 times root of 5. And that's a number for the side length of the regular pentagon. Okay, that's the side length of the regular pentagon. Okay, now here's the magic. In the previous page, I just proved, so remember the number. Okay, try to remember the number. It's a 1/2 times the square root of 10 minus 2 root of 5. Let's go back to the previous page. What is that number? The number is the same thing. Can you see that? This number is just 1/2 the square root of the 10 minus 2 times root of the 5. So that means the green light here, right? The green edge. So that edge just give me the side length of the regular pentagon. And then you can just use this one to cut from the unit circle, and you can construct the regular pentagon. Does it make sense? Right? That's a name for the regular pentagon. So we are done. All right. So far we have finished the following. Right. So what are the constructible? So some of the n can be constructible. So let me summarize here. Okay. So let me summarize here. Some of them can be constructible. Okay, constructible. So let's see. Constructible. Okay. Constructible regular polygon. Okay, when n is equal to 3, certainly is good. 4 is good. 5 is good. 6 is good. Why 6 is good? Because you can do the for the 3, and then you can do the midpoint, right? Basically, right? 7 is actually not good, so not constructible. Not constructible when n equals 7. 7 was not good. 8 is good because the 2 times 2 times 2, right? 9 was not good. 11 was not good. 12 is good. Why 12 is good? Because 6 is good. If 6 is good, you just cut that into half and half, right? So 12 is good. 13, I believe that's not possible. Okay. And 14, that's not good. 15 is actually good. All right. 15 is actually good. So this is actually a good one. Right. Why 15 is good? It's a little bit hard. We can't go over that today, but 15 is good. Right. Anyway, so some of the numbers are good, some of the numbers are not good. Right. Okay. 16 is easy. Right. 16 is just a 2 times 2 times 2. 16. So let's see. So 16 is good. 17, I want to emphasize that this is a huge, huge, huge number. Okay, a huge result. Okay, so 17 is very very good. Okay, so 17 is good. Who did that? Well, actually, that was done by Gauss. Okay, that was done by Gauss in 1837. Okay, that was about 200 years ago. Okay, we're less than 200 years ago, but we're 180, right, around that. 180 years ago, about that time. So uh, when he did that, he was very young. He was about just like 17 years old. So a 17 years old student construct a regular polygon of side 17. That's remarkable. That's remarkable. Okay. And I can tell you that when I was young, like your age, my mathematics teacher actually told us how to do that. He spent like 1 hour to construct that regular polygon of 17. And in the entire board, basically, going from the left upper corner to the right lower corner, the entire board was a construction of 17. Okay. It cost us 1 hour to do that. Anyway, so we cannot do it today. And if you're interested, you can search the internet. It tells you how to construct that. Okay. So I'm gonna finish that for the construction. So are there any questions? So I'm done for the construction. It took us 3.5 lectures to eventually finish everything for construction. Any question? Are there any questions? Are there any questions? Okay, if there's no question, I'm gonna move on. Let's move on. So let me go over some homework problem. Okay, let's go over some homework problems. So one of the homework problems some time ago is the following. We want you to prove that basically, let me check. Where is it? Where is the problem? I think somewhere earlier. I can't find it. Oh, okay. So here it is. Here it is. Suppose A, B, C, D. So this is a homework 5. Let's do homework 5. And question number 3. Okay, question number 3. Okay, so assume that A, B, C, D is a cyclic trapezoid. So we got a trapezoid here. Okay, and then we get the 3 here, 4 here, and then we get a 6 here. All right, so let's see. So this is a trapezoid. So we have the A, B, C, and D here. All right, and we know that then let's say AB is parallel with the CD. Okay, and this is 3, this is 4, and this is 6 here. And my question here is that I want to figure out the, wait a second, AB, wait a second. So this is B here, C, and that's a D. Okay. So A, B, C, D. All right, so we can get that. And then my question is that I want to figure out that what is the CD. Okay, so what is CD? Okay, just give everyone a few seconds. Actually, for this question, some of the informations are redundant. I don't need all of this. I have the 3, 4, 3, 4, 6 just to try to confuse you. So 3, the number 3, the number 6 is redundant. I don't need that. Okay. The answer is actually 4. A, B, and C, D are actually the same. Okay, why they are the same? Okay, why they are the same? So okay. So I want to prove that. I want to prove that A, B, and C, D are the same. So that's my original question. But since it's online submission, I cannot ask you to prove online. So that's why I changed that to a numerical problem. So the actual problem is I want you to prove A, B, and C, D are the same. Okay, why? Let's think of that. So in other words, 6 and 3 are not important. I don't need that. So I just don't need that. I don't need that. It doesn't matter. Okay. It doesn't matter. Okay. So what is this? How do I prove this? How do I prove this? Okay. um, where first I'm gonna do this. Okay. I'm gonna draw let's see. I'm gonna draw a, a parallel line with the AB. So let's say A, B, C, D, E. Right. Okay. Okay. So proof. I'm going to draw DE parallel with the AB. Okay, DE is parallel with AB. So if that's the case, this implies that A, B, E, D is a parallelogram, right? Because you have the two opposite sides, they are parallel with each other. So if it's a parallelogram, and I think sometimes ago, did we prove that? I think in 07 geometry, right? We proved that an AB is equal to the DE, right? For parallelogram, the two opposite sides are congruent. So AB is shifted into the DE. And so I just need to show that for the small triangle, it's an isosceles triangle. If I can prove it's an isosceles triangle, then I'm done. Okay, well, how do I prove it's an isosceles triangle? Well, I have to prove that their two base angles are congruent. So I want to show that this angle and that angle, they're congruent. They're congruent. Okay, how? Okay, give everyone a minute. How do you prove that the two angles are congruent angles? And keep that in mind. The ABCD is a cyclic quadrilateral. Okay, for cyclic quadrilateral, I believe, let me show you sometimes ago. I think at that point, we give you at some point. Okay, so here is what we did here, right? For cyclic quadrilateral. So ABCD is a cyclic quadrilateral if the opposite angles are supplementary. The sum of the opposite angles is equal to 180. So that's the theorem we're going to use today. Okay, so let's go back to here. So ABCD is a cyclic quadrilateral if and only if the sum of the two opposite angles is 180. Okay, so can you use this to prove this? Well, so let's see how we can do that then. First of all, I'm going to have the angle C, right? Angle C and angle A are supplementary. So I have angle C is just 180 minus angle A, right? Angle C and angle A, they are supplementary. Okay. But also, what is the 180 minus angle A? Where A and B are also supplementary because the parallel line. Can you see that? AD and CB are parallel. Oh, my condition was not right, so that should be. So it should be the AD is parallel with the BC, right? So because of that, that's the angle of the B. So the reason is that AD is parallel with the BC, right? So the top line and the base line, they are parallel. That means angle A and angle B has a sum of 180. So angle B and angle C are actually the same. And also, I can switch the angle B into the angle of DEC into just this angle here. The angle I'm looking for here. Again, this is a parallel line. So the reason for this is the condition here. DE is parallel with the AB. And then we are done, right? The left-hand side is the angle C. The right-hand side is the angle of the DEC. And this implies that this is an isosceles triangle. And therefore, if it's an isosceles triangle, then we can get the DE equals DC. And then we are done, right? So both of them together, that means I get AB equals the C and D, CD. Okay, so just give everyone one more minute. It's a very nice proof. Very nice idea. Okay, give everyone a minute. Let's go over the proof again. Are there any questions? Everyone's good? Excellent. Now I'm going to work for today's theorem. Today's theorem, we are going to talk about the power of a point in a circle or outside the circle. So anyway, so here is for today. We're going to talk about the power of a point. The power of a point. So we are done for construction, all right? If you're not comfortable with the construction, now it's the beginning of the new topic. Okay, so don't worry about the previous one. We just finished that. Okay, so it's a new topic, the power of a point. So how do you define the power of a point? Okay, so first of all, I'm going to give you a theorem. Here is a theorem. Okay, here's the theorem. And suppose we have a circle. All right, suppose you have a circle and you get a point here. All right, point is a P here. And you want to define the point of P. Okay, well, so you might say, well, the point of P, I'm going to define the point of P in a following way. So let's say, suppose I get all right, so let's see, I get that one here, right? Or maybe I can get the other one here like that. Right, wait a second. So let me just erase one of this. So suppose I just go through the P, I draw a chord, all right? So it doesn't have to be a diameter. It can be anything. It's just a chord, okay? So this is A here. Oops. So this is A here, and this is B here, right? So I want to define the power of a point in the following way: is a PA times the PB. I want to define this is the power of the point. The power. The power of the point P. I want to define that. Okay, so what's the power of point? The power of point of P is defined to be the PA times the PB. And then you can say, well, where's the A and B? A and B can be anything, any chord. And you might say, well, what? If I choose a different AB, is the product still the same, right? In other words, if I just say, okay, so let's do a different chord here. Suppose I have C here and D here. And according to the definition, you're saying that the PC and PD, this is also your definition of the power of the point P, right? And so you say, oh, you may have many different definition, many different ways of the definition, right? Because you can define many different chord here, right? You have a chord here, and you have the product. So the question here is that Or I may have infinite many products. So the question here is that are all of those products the same, right? If they're different, then I'm in trouble, right? So I have to prove that those products have to be the same because if they're different, that's a very bad definition, right? In mathematics, when you have a definition, the definition has to be unique, right? You have one way to have the power of p, and you have another way to have the power of p, but I'm going to show that the two products are the same. They are always the same. So that means it doesn't matter which chord you choose, right? You choose any chord, right? It's like just like when you define the slope of the line, right? It's defined by choosing the 2 points from the line, but the definition does not really depend on the 2 points you choose. You choose any 2 points, you get the rise over the wrong, and you get the same ratio. And that's similar idea. So you can choose any chord here, A, B, or C, D. It doesn't matter. You pick the product of the two nine segment, and the product is always the same. So that's something I want to prove first for today. Does it make sense? So that's the definition for the power of point. And so that it really doesn't matter which chord you choose because your product is always the same. Okay, I'll give everyone a minute. Let's see how to prove this. Okay, let me give you a hint. The hint is to use the similar triangle. So I'm going to give you the hint. Let's say I'm going to connect the AD and connect the CB. All right, try to use a similar triangle and to finish the proof. Okay, so I got the two triangles and I want to show that the two triangles are similar triangles and I set up the ratio because they're similar, right? And so when you organize the ratio, eventually you get the two products to be the same. Okay, give everyone a minute. So 1 or 2 minutes. Okay, let's try that. So how can you prove the two triangles are similar triangles? So let me first give you the write down the conclusion, and I give you the time to prove. So prove. I'm going to connect the AD and connect the BC. All right. The idea is how to prove the triangle of PAD. Okay, is similar with the triangle of the PCD. Okay, can you tell me why the two triangles are similar triangles? Okay, anyone can show me why the two triangles are similar triangles? Where we can have the corresponding angles to be the same, right? So is this angle the same as that angle? Oh yeah, they are inscribed angles, right? They inscribed to the same chord, to the same arc, right? It's an inscribed angle theorem, right? So just because first of all, I get that the angle M is half of the BD, the arc of BD, and this is the angle C. So we get one angle, one pair. The other pair, same thing. The angle D is one half of the arc of the measure of the AC, and that's the same as the B here. So that's the reason, right? So that is the reason, right? So we got that. So because of that, we have the two triangles are similar triangles. And if the two triangles are similar triangles, can you write down the ratio of their corresponding sides? Okay, I invite you to write that. Give you everyone 10 seconds. So if the two triangles are similar triangles, can you write down their corresponding sides? Okay, they should have the same ratio, right? All right, so that means I'm going to have the following. So I will have the PA, right? So the PA, right, correspond to PC. Does it make sense? PA is here, correspond to the PC, right? The two sides are corresponding side, right? PA and PC are corresponding. And then similarly, PD correspond to PB, right? PD and PB are corresponding. And then we finish the proof because we get the same ratio, right? We get the same ratio and then we get the cross multiplication. So do the cross multiplication. We get the PA times the PB equals the PC times the PD. That's excellent. That's one of the nice, very nice theorem in terms of circle, right? For every for given point P, no matter what kind of core you have, right? The product of the two parts is always a fixed number. And that's called the power of the point. Okay, give everyone a few seconds. Try to understand the proof. Not only you remember the conclusion, but I want you in geometry, you need to understand the proof. If you don't understand the proof, it doesn't mean, it doesn't mean anything, right? You just didn't know about geometry, right? Geometry, you do need to know how to prove. Okay, everything's good. All right, so we get the PowerPoint when the point is inside the circle. And then the next question is that what happens if the point is outside of the circle, right? What happens if I get a point outside the circle? So what can I do? All right, so I have a next theorem. So my next theorem is here. Again, it's a theorem. So my second theorem for today. So this is the first theorem, theorem 1. Okay, my second theorem for today is, so theorem 2. It means that, okay, where I get a power, I get a point outside of the P. Okay, how do I define that, right? So let's see. I'm gonna get, again, I get a circle here, and I get the point outside. So let's say P outside. How do I define the point of P if P is outside of the circle? Okay, well, let's just do the same thing. So I'm gonna do, let's see, I'm gonna have, all right, so let's say P, B, and C, right? Again, you get any cut, right? Any cut here. It doesn't have to be a diameter, just anything. So you go from a P and you draw any straight line intersect with a circle, all right? And what I want to do is that I want to prove I want to define PB and PC, the product, as the power of P. So that's my definition. I want to define that. And again, people say, oh, wait a second, what happens if I draw a different line, right? So if I draw a line in the other way, right? BC, and maybe this is D here, this is E here. So can you still define that PD times the PE, right? I also define this way. This is the power of the point P, right? So if you want to define the power P as a product of the PB and the PC, and you have to prove that the two products are the same, because otherwise it's a very bad definition, right? So it really does not depend on what line you want to choose to go through the P, right? Any line is fine because the two products are the same. Okay, so let's think of that. How to prove they are the same. Give everyone some time. Let's think of that, the strategy. The strategy is very important. All right, let's think of that, the strategy. So I want to show that the two of them are the same. Okay, how to prove this? Similar triangles, right? If you look at the previous proof, you go from here, you generate two triangles. You want to prove the two of them are similar. And now I'm going to give you a similar idea. So let's say I'm going to connect this, okay, and connect this. All right, so that you have two triangles, okay? So let's see. So here I'm going to write down the idea. The proof is here. I'm going to connect BD, and I'm going to connect the CE, right? So how do I prove this? I get two triangles, right? One triangle is the, let me give you the green one. I want to show that this green triangle is similar to the other triangle. Let's say the yellow one, okay? Here's one green triangle, here's a yellow triangle. I want to show that the two triangles are similar triangles. Everyone understand what I mean here? Okay, so all I want is that I want to show, I want to prove, I want to prove that the triangle of the ABD is similar with a big triangle. Okay, which one corresponds to which? A, B, C. Okay, why? Okay, so let me give everyone 1 or 2 minutes. You need to finish my proof. Okay, let's see how to finish the proof. Give you a suggestion. Just the problem we did here. That's the theorem we are going to use. All right. If ABCD is a cyclic quadrilateral, the opposite angles are supplementary. Okay, the opposite angles are supplementary. That's the theorem we're going to use today. Okay, that's the theorem we're going to use today. So let's see. All right, so let's see. We get the how can we do that? You see that? So you get a quadrilateral, right? This is a cyclic quadrilateral. You see that? That's how we need that. So we get the BCED is a cyclic quadrilateral. Okay, you finish the proof. It's almost there. I give you all of the hint already. All of the hints are here. So let's see. Because BCED is a cyclic quadrilateral. Okay. That means I have angle C plus angle, let me use here for the angle 1, and this is angle 2. Angle C and angle 2 is equal to 180 degrees, right? And now, on the other hand, angle 1 and angle 2 is also 180 degrees, right? So that means, what does that mean? That implies the following. Angle C is 180 minus angle 2, and that's equal to angle 1. So that's the way you get the pair of congruent angles. Okay, let me repeat that. I want to show that angle C, okay? I want to show angle C is equal to angle 1. That's one pair of the congruent triangle. Why? because angle C is supplementary with angle 2. And angle 1 is also supplementary with angle 2. So that's the reason angle 1 and angle C are congruent. Okay? And can you find another pair? Well, another pair is just angle P by itself. We're done, right? Or you can say that, let me, if I don't want to use the angle P, can you show that similarly? Actually, you don't need that because I get angle P already. But I want to give you, because this is very important. The theorem is very important. Angle E is the same as the angle. Let me put the 3 here, angle. So that's the angle E should be the other one here, right? So let me put the angle of P, B, and D. It's the same argument. Can you see that? It's the same argument. Right. Okay. So that's the reason. So I got that, right? And after I get this, then what can I get? I will have the following ratio are the same. Okay, so what can I get is that I have the wait a second, where is the A? No, I mean the P is not the A. That's not A. There's no A here. It's just a P. Okay, so that's a P, BD, and PEC. Okay. Okay, right? So the two triangles are similar triangles. All right, and then we are almost done. Why we are almost done? Because because we have the similar ratio, right? The ratio are the same. So we have the PB over, PB is here, P over the PE, right? Equals the PD, right? PD over the PC, right? Okay, and then you do the cross multiplication. So that means you get the PB and PC, right, equals your PD and PE. So we are done, right? So this one just says that we can define the power point P if P is outside, right? It's just a PB. You just draw any straight line intersect with a circle, right? And then as soon as it intersect with the circle, then you get the product, right? Then you get the product. Does it make sense? Good. Okay, give everyone 1 more minute. The proof are very, very tricky, right? If some of you are not familiar with that, it's fine. I think many of you are not familiar with this. That's okay, and you just keep on working, right? Just keep on working, try to understand that, right? And then later on, we're going to we'll be okay with that. I would say that this kind of technique is just standard, but just because it's the first time to understand that, it's a little bit hard, right? But later on, you will be able to understand that. Okay, not a big deal, not a big deal. Okay, so just give everyone 1 more minute. I slowed down a lot actually today. Okay, and I'm gonna give you a coronary. Okay, I'm gonna give a coronary. Okay, so here's a good coronary, where when you define the power of the point, right? Suppose it's outside, right? It's outside here, and then you get the P is here, and then you have a direct straight line here. And what happens if you want to draw the a tangent line? So suppose this is tangent, right? This is A here. Then I want to prove that PB times PC is actually the square of the PA. Okay, PA is a tangent. Okay, if PA is a tangent, then this is the definition for the PowerPoint. So the PowerPoint is actually square of the PA. Okay, why? Why this is the case? So I want to give everyone a minute. You can just get that. You can just get that directly from the above. Can you see this? We're imagining that. Imagine that. So because let's see. So here's a proof, right? So let's see. Well, let me give everyone a minute. Let's try it. Why this is a square of the PA? Just imagine that you have the one line is a PBC. You fix a PBC. The other line PDE. You don't just look at it as a fixed line. You look at it as a dynamic line. So your second line is moving outside. Okay, but if you swipe outside, at some point it becomes a tangent, right? But when it becomes a tangent, where are those D and E? D and E are just becomes the A here. Can you see that? Right? Can you see that? Right. So that's a reason. But anyway, so here's a quick proof. I can give you two different proofs. One proof is that so the first proof is proof one. Proof one, you can say where PC times PD, I can just draw a different cut line that way. So B, C, maybe D, and E. According to the previous theorem, we get the PD times the PE. But now I'm gonna rotate. Okay, I'm gonna gradually rotate. So rotate PDE outside. Okay, I'm gonna just keep on rotating. Right, I'm gonna just keep on rotating in this way. Right, you're gonna rotate that. So if you rotate this outside, keep that in mind. The product is always correct. Right, it doesn't matter the position of the PDE, right? It's in any cut line. So I just rotate that, continue to work on that. At some point, certainly it becomes a tangent line. So when it becomes a tangent line, then it is just a PA square. Can you see that? PD becomes that. So when you make a rotation, eventually, the D will becomes A, and E will becomes A. So that's why PD times the PE is the PA times the PA. So that's a square. All right, that's a square. So that's the first proof. You can prove it that way. Another proof, if you don't want this proof, that's okay. We can prove directly by using the similar triangle. Okay, so we can prove directly. So let's say proof two. Let me draw the picture again. I'm gonna get that picture. All right, so let's say you get this one here. That's a P, that's a B, that's a C, and this is a tangent line A here. So what I can do here, I'm gonna connect this one and I'm gonna connect the other one here. So that's my second proof. Proof two. All right, you're gonna try to use, here's the idea. You're gonna prove that the PAB is parallel. So PAB is parallel with the PCA. So in other words, you have two triangles, right? So one triangle is the green triangle here, right? And then the other triangle will be the yellow triangle. So I'm gonna get the yellow triangle here, like that. And you want to show that the green triangle and the yellow triangles are similar triangles. Okay, can you do it? Give everyone a minute. Actually, you don't need a minute. So why the two triangles are similar triangles? Well, this is a theorem actually we needed sometime earlier. Let me try to get that somewhere. In our previous lecture, try to figure out where it is. I believe it's somewhere here. Yeah, I think that's here. So if you have, it's a coronary one, okay? So this one basically says that if you get a tangent line, if you get a tangent line, okay, if you get a tangent line, this angle is the same as that angle here, right? The two rate, the rate angle here, this one and this one, they are they are similar. They are the same. They are congruent angles. Okay, everyone understand that? So if you have this one here, now let's go back to here. So if that's the case here, it basically says that this angle is the same as that angle here. The two angles are congruent angles. Okay, why the two angles are congruent angles? I'm going to show you the proof quickly. So first, we can say that the angle of the PAB is just half of the angle, half the measure of the AB. And half of the measure of the AB is just the angle of C, right? So the two of them are the congruent. And then the other one is certainly B angle P and angle P. The two of them are, so we have the two pairs of congruent angles. We get that. That's the reason why we get that. Okay. And if that's the case, then we can I can write down the similar ratio, right? The similar ratio. So the ratio here is the following. I get the PA over PC. Okay. And that's equal to the PB over the PA. So that implies that the PB times the PC, that's the PA square. It's a cross multiplication. All right, and I finished my proof. So just give everyone 1 more minute. Let's go over. Let's go over the coronary again. I give you two different proofs, right? One is you can just use the formula the directly, but using the other line considered as a dynamic line. It's not fixed line. So the other line is moving, keep on moving until it becomes a tangent line. Okay. Second proof is a direct proof. Okay. So just give everyone 1 more minute. You still have time. Okay. I'm gonna give you one more problem for today to finish to make use of that. Okay, so let me give you one more problem for today. So here's an example. Okay, so for this one here, a circle here, and now we're going to get something. All right, so you get the P here, Q is here, U is here, R, M, S, and T. Okay, so assume you have the following. You have this is your X value, and X value. So the three sides are the same, the X value. Okay, and this is Y, and this is Y. Okay, the two Y's are the same. Okay, and let's see, MT is equal to 2. This side is 2 here. MT is 2. And MQ is equal to 8. You get 8 here. Okay, so the question here is that I want to figure out the Y. So I want to find the X value and find the Y value. Okay, give everyone a minute. All right, so I have only 1 minute left, so let's try to finish it fast. First, I'm going to work on the power of p. So if I work on the power of m, right? So from one side, I get x times x squared. From the other side, it's 2 times 8. That's equal to 16. You see that? I work for the power of m. You have two chords. One chord is x times x. The other chord is 2 times 8. So 16. So that means x is equal to 4. So that's one value. Now to get the value of y, I'm looking for the power of p. The power of p. So that is this point here. Right. From one side, the power of p is x times 3x. You see that? So one side is x, the other 9 sigma is 3x. So x and 3x. And from the other one here, it's y times the 2y, right? And then you get almost that. So that's a 2y squared. This is a 3x squared. So what is the y? Y is equal to 3x squared divided by 2, take a square root. And then you get the x value, so you get the y immediately. All right, so that's all for today. Okay. All right, I don't have time. I have to log out, and I have another class immediately afterwards. So next time we don't have a class because of Easter. So I'm going to see you in 2 weeks. Okay, bye everyone.